Hello everybody and welcome to Circuit Analysis 1. We're continuing our study of AC circuit analysis using the same principles we learned when we studied DC circuits. This section is a little different. It's important to study the topical subjects, and I tried to list these in the slide where you find them. So if you get into a situation where you have to learn about something, go over these sections and learn them to get more acquainted with them. The capacitor, we're going to start there. There's three main passive elements in electrical engineering: the resistors, capacitors, and inductors. Some may argue that also diodes should be included here, but that'll be discussed in another class. So a capacitor is a device that's comprised of two plates that charge up, and they store the charge. The units for this device is called a farad. The higher the value of farad, the more charge it can store. Material called a dielectric is inserted between the plates, and that will control the amount of electric field buildup between the plates. On most printed circuit boards, you will notice a capacitor between power and ground on the integrated circuits. And why is this? This is to keep a smooth DC voltage by suppressing any voltage spike and minimizing the DC ripple. Some capacitors are polarized and must be inserted correctly into the circuit. If we look at these pictures here, these are not polarized, but these cans are, and you'll notice the black stripe indicating that this terminal is negative and should be inserted in the circuit correctly. So remember, a capacitor can store energy and it can return it back to the circuit. Resistance in an AC circuit opposes the flow of charges. A capacitor has something that we call capacitive reactance, and there's the formula given for it right here. And the units of measure on that formula is ohms. A capacitor is a function of frequency, as we can see. The angular velocity can be converted to 2 pi f times c, the value of the capacitor. So it is a function of frequency, and also, using that idea, it can block DC voltage, because at a low frequency, or as we might say in mathematical terms, as the denominator approaches zero, the answer becomes infinity. So infinity resistance is very high and can be seen as blocking. So in other words, a capacitor is often used for stopping the passage of direct current from one circuit to another while allowing alternate current to pass. But here's the formula for capacitive reactance. X sub c in ohms is 1 over the angular velocity, or we could say 2 pi f times c. So it's inversely proportional to frequency. As the frequency goes up, X sub c goes down. Frequency goes down, X sub c goes up. An inductor is a coil of wire. And that coil of wire can be wrapped around a hunk of metal. And this creates a magnetic field. So the units of measure for an inductor is henries. You buy an inductor in the units called henries. The value of inductive reactance is proportional to the frequency. Here's the formula. X sub L in ohms equals the angular velocity times L, or 2 pi f, the frequency, times the value of the inductance. So as frequency goes up, X sub L goes up. It's directly proportional. As frequency goes down, X sub L goes down. And commonly a choke inductor is used to block higher frequency of alternating current in a circuit, but it'll still allow the low frequency or direct current in that circuit to pass. That's the use of a choke. So notice that reactance can be either inductive reactance, X sub L, or capacitive reactance, X sub c. And that'll X sub L and X sub c, the units of measure is ohms, and it will oppose the flow of charge in an AC system. And we can use Ohm's law when we get that value of ohms. Let's get some experience computing reactance. Let's go through some examples of X sub L here. If we have an inductor of 200 millihenries, We have an angular velocity of 100 radians per second. X sub L is the angular velocity times the inductor, and that equals 20 ohms. Now, if we use the same inductor and we go to a higher velocity or higher frequency, we get a higher resistance of 20K. So we could write the inductor value here, 20, as a polar coordinate. A polar coordinate is the same as a vector or a phasor. And then we would say that this is 20 at 90 degrees. If I had to write it in rectangular coordinates, it would be plus J 20. And the units is ohms. Now, why J? Because in electrical engineering, I is used for current, so for the imaginary line, we use J. For the second example, 20K ohms, we could say it's 20K ohms at plus 90 degrees as a polar coordinate, or we could write it as plus J 20K. So let's go through an example here with capacitive reactance. So we have the angular velocity of 377 radians per second. We have a 1 microfarad capacitor. So we multiply those on the denominator and we do the inverse there. We get 2,652.5 ohms as our answer. Now, if we have a higher frequency of, say we just have a frequency, not an angular velocity, higher frequency of 6K hertz with a 2.2 microfarad capacitor, I can plug 2 pi f in there and put 6K in there, and I get 12 ohms. Now, how would I write those as vectors? This would be 2652.5 ohms at minus 90 degrees for the capacitor. So remember, the inductor is plus 90, the capacitor is minus 90. If I wanted to write that as a rectangular coordinate, it would be minus J 2652.5 ohms. In the second example, 12 ohms, it would be 12 ohms at minus 90 degrees for a polar coordinate. Or we could say minus J 90, minus 12 J. Minus J 12, I should say, for the rectangular coordinate. So polar values, why do we have to know the difference between polar values and rectangular? Because polar values are used for multiplication and division. If we have to add and subtract, that's when we go to rectangular coordinates. So we have to go between both of them. So let's go through this example. I'm given a voltage expression here of 10 sine omega t plus 20 degrees. That vector is 10 at 20 degrees. Now, if I want to determine the RMS current, and this circuit has a 500 ohm resistor, I'm going to first convert this to RMS. So 1 over the square root of 2 equals 0.707 times 10. And my vector now is 7.07 at 20 degrees. That's voltage RMS. Divide the RMS voltage divided by the resistance, 500 ohms at 0 degrees, because there's no phase shift in that resistor. And what I get here is I divide the magnitudes, 7 divided by 500, and I subtract the angles, 20 minus 0. So I get 14 milliamps at 20 degrees. There's no phase shift between the current and the voltage with a resistive circuit. Let's do another example. So I'm given a voltage here of 10 sine 2000 pi is my angular velocity plus 20 degrees. My vector here is the peak value of 10 at 20. If I want to calculate the RMS current, I'll convert this to RMS first of all. 1 over the square root of 2 is 0.707 times 10. So I get 7.07 at 20 degrees as my vector. Now I want to determine what my x sub c is. And so I'll use that times the angular velocity. Here's the angular velocity, 2000 pi, times the value of 400 microfarad. And I get 4 ohms at minus 90 degrees. The capacitor is at minus 90 degrees. Now I'm going to use Ohm's law, voltage divided by resistance. This resistance is the capacitive reactance. I divide the magnitude, 7 divided by 4, and I subtract the angles, 20 minus negative 90, and that gives me 1.77 amps at 110 degrees. And we should, if we looked at this at 20 degrees here and plus 110, we see that the current leads the voltage in a capacitive circuit. Let's do this example here with an inductor. I have a 200 millihenry inductor, and here's my value here, 10 sine of 2000 pi is my angular velocity plus 20 degrees. So I'll write that as a vector, 10 at 20 degrees. And if I convert that to RMS, here's my RMS vector, 7.07 at 20 degrees. Now I'm going to calculate my x sub L, and that is my angular velocity, 2000 pi, times my inductor value, 200 millihenries, and I get 1.26 K at 90 degrees because the inductor is a plus 90. So then I'll use Ohm's law, V divided by the resistance, which is x sub L, and I divide the magnitude, 7 divided by 1.26 K gives me 5.61 milliamps. 20 minus 90 degrees gives me minus 70. So there's my current lags my voltage here in this example, an inductive circuit. All right, so I'm given a purely resistive circuit. I shouldn't see any phase shift here. Here's my value, and here's my value of my resistor in the circuit. So if I want the current RMS, I'll use the voltage RMS, use apples with apples and oranges with oranges. So I convert that to 4.26 at minus 40 degrees. Divided by the resistance, 110 at 0, because there's no phase shift with this resistor. So minus 40 minus 0 gives me minus 40 degrees. 4 divided by 110 gives me 38.56 milliamps at minus 40 degrees. So voltage and current have the same phase. Something to remember with AC circuits of polar coordinates. A purely resistive circuit has no phase shift between the voltage and the current. The current and the voltage are in phase. A purely capacitive circuit or load has a electric field properties that cause the voltage and current to be out of phase by 90 degrees, and it's minus 90. The current leads the voltage. A purely inductive circuit has a magnetic field property that causes the voltage and current to be out of phase by 90 degrees, positive 90, and the current lags the voltage. So if we look at in terms of the current, it leads the voltage in a capacitive circuit, and it lags the voltage in an inductive circuit, and there's no phase shift in a purely resistive circuit. Here's another example. If you're just given x sub L in ohms already, we can do our work. Voltage divided by resistance, and we subtract the angles, minus 40 minus 90, they get minus 130, the current lags the voltage. And here's another example using a capacitor. It's already given us the value in capacitive reactance, and we got the RMS voltage, voltage divided by resistance. 4 divided by 100 gives me 42.4 milliamps, and I get minus 40 minus negative 90, and that gives me a positive 50. Current leads the voltage. So for homework, do these 3 problems, and I'll post the answers for you. And because we're doing this because of our time crunch, and just do these 3 problems, it'll help you explore and understand this material. See you next time.